And today's session is going to be on the Azure Machine Learning Service, and really a fairly high-level iteration of that, because it is quite a complex resource that targets people with little to no machine learning experience, all the way up to people that are expert data scientists. So really like high level, so that all the folks in the audience can relate and start leveraging some of the services for their use case. And a bit about myself. My name is Pratheek Deveraj. I am an AI solution architect for Microsoft, and I am based out of Vancouver. And I generally work with accounts across Western Canada. And Western Canada, in our sense, would be anything from Victoria all the way to Manitoba. So anywhere in that region are some of the accounts that I work with, and very likely I may have worked with some of you in the past, directly or indirectly. And let's get started with this. Start with a few slides first, and then we'll go straight into the Azure ML service and show you what that portal looks like, and also go through some of the SDK components as well. So within Azure AI, there is three main pillars. So we have the apps and agents, AI apps and agents, which cover the bots, chatbots, and then we have the Azure Cognitive Services, which is essentially pre-built APIs that you can leverage by performing submitting a simple payload to URI, and then it returns back with some response. So some examples of that could be something like, say, using computer vision to detect objects in an image. So you pass on an image to that endpoint, and then it returns back with bounding boxes and predictions of various different objects in that image. Or it could be something like OCR, or speech to text or text to speech type operation. But of course, that won't be the content for this presentation. We're just going to be primarily focusing on the Azure Machine Learning Service. And our second pillar, you can see that the machine learning itself is comprised of Azure ML and the Databricks, Azure Databricks. Both of these have their own unique workspaces. And depending on the type of workload, you may be wanting to work with Azure Databricks if you're doing some sort of ELT, ETL, working with lots of data, streaming data, then maybe Databricks would be the choice of workspace for your workloads. And you can always install the Azure ML SDK. So it's not limited to any particular service or operating system, because you can install it as you would with any other Python library. You can always install the Azure ML SDK within a Databricks cluster and still leverage some of the model tracking, model management, all within Databricks or any other environment that you want to, that allows you to install Python library. So it's more or less two components to it. One is an SDK, Python SDK, and there's also the R SDK, and then there's the visual interface, which is basically a web portal where you can perform all your machine learning, spin up your Jupyter Notebook servers, and so on, all within that particular endpoint. And for the final column, we have the Azure Cognitive Search. And this service is more of knowledge mining type service, where you can leverage some of the skill sets from the cognitive services, such as your OCR or your speech or your computer vision APIs, and then use that to break down unstructured data or like PDF documents or any other large volumes of unstructured data and make meaningful use of those. And that's another category itself. So generally there are three categories. These are just plug and play. The apps and agents are mostly APIs. And then the bot framework is more of a framework where you can build bots using like multiple languages. Now we support Python, but originally it was a C# based implementation. But we do support a lot more languages, JavaScript, and you can seamlessly integrate some of these cognitive services along with the bot. For example, by adding what's called LUIS, Language Understanding Intelligence Service, which provides you a way to customize utterances that are coming from users and then extract certain queries from those utterances and then make some actionable decisions because you understand the context of a user query better. So that can be a different session on its own, but today we're just going to be focusing on the Azure Machine Learning itself. And I sort of went over the cognitive services already, but they're generally broken down into 5 major categories. One of them is the vision, like all the computer vision category of APIs. Some of them include facial recognition, identification, object detection, and OCR, as I mentioned earlier. And you can also perform metadata analysis on audio and video as well, and extract like celebrities or capture notable faces, popular like athletes in a video stream, and tag the times where those faces were detected. So really, it's up to you how creative you can get with using some of these APIs. And within speech, there's of course like speech to text, text to speech, custom speech, custom language models that you can train on, where you can recognize industry-specific terms. For example, if you say AKS, the model would not know what that is. But if you pass on like a custom speech model stating that AKS, the acronym stands for Azure Kubernetes Service, then it will learn to understand that, and it will translate that accurately once you apply that custom speech model. And of course, there's more as well, like language understanding with sentiment analysis, knowledge extraction, and a whole plethora of services with Bing image and video search APIs. But just wanted to give you like what's possible, because oftentimes when you're working with ML models, you don't have to build everything from scratch. You can always leverage what's already available, just like you would download like a Python library that's available in like a public GitHub repo. Similarly, you can start using some of the cognitive service features rather than building your own OCR model, which is quite complex and requires dozens of people to be working on it. Whereas you can just plug and play and use one of these services depending on the use case or scenario. And yes, we're going to continue focusing on the Azure Machine Learning for the rest of the session. And the Azure Machine Learning itself is a combination of the Azure infrastructure. So you can leverage, if you need like a high performance compute, you can choose a compute cluster of CPU computers, or you can use a GPU if you're doing some sort of learning, natural language processing, or some sort of custom vision type work. Then you can use the appropriate GPUs. And of course, it combines with the Python SDK itself, which is something that you can install as you would with any Python library using pip. And we also support the R SDK as well. However, the R SDK is slightly behind the Python SDK in terms of full functionality, but you would be able to use both languages for your data science workflows. And the reason why we support R and Python and not C# or JavaScript is because most of our customers that I worked with generally either perform data science workloads in Python or R, simply because there's plenty of people, like thousands, hundreds of thousands of people using these libraries, and very few people may use something like C# or Java for their ML workflows. And together, what you can do is build end-to-end machine learning workloads where you can prep the data, perform feature engineering on that data, build your models, retrain your models, manage the models, register them. If you think that your model is performing at a certain threshold, you can register those models. You can track your experiments and see how you've been progressing throughout the iteration of model training. And finally, you can deploy the model to an Azure container instance or in a production setting to AKS, Azure Kubernetes Service, all within that single SDK. Like that SDK allows you to communicate with the Azure infrastructure and the Azure Machine Learning Workspace and perform your full end-to-end tasks, whether it's on your local laptop, it's operating system agnostic, so you can execute that SDK on any OS, and or on the actual website itself, which I will get into once we get to the demo stage, and perform this whole orchestration all within that single resource and that single SDK. And in a typical machine learning process, you have various different steps. Some steps involved, majority of the time you're going to be dealing with preparing the data and feature engineering. And you can use various different IDEs and OS, so it's agnostic of any platform or IDE. And you can, of course, perform your training and testing on the appropriate hardware or infrastructure that makes sense depending on the type of algorithm that you're using. And you can, of course, register and manage your models, build Docker images, and service that Docker image in some sort of compute. And the Azure Machine Learning itself, if I could break it down into 3 categories, it would be from the most automated, for I guess in terms of skill level, basic, you don't need any background in data science, to advanced, which would be machine learning notebooks, the SDK, and like code-based approach. And the intermediate would be like a visual drag and drop type interface. So with I'm just going to play a small clip of video that's embedded into this slide. You can see that with the automated ML, you can use the UI, like the website UI and the Azure ML portal, to upload a data set. And from there, click start, and it pretty much will do all the work for you. It'll do feature engineering, selecting the best parameters, and so on, fully automated. And you don't have to have any background in ML to leverage an automated ML component of the service. And if you're a little bit more experienced, you can always use the visual interface. And this is more like a drag and drop type approach, where you can perform that exact same type of experimentation, where they're trying to do some form of classification the same way. The only difference is you have to select all the pieces, like the moving pieces, like the data source, the features of the data that you want to use, some sort of feature engineering steps, and then the model parameter. You can control all of those, but you don't have to write any code. You can just drag and drop using the visual interface, which we call as the AML designer. And finally, for people that have more experience, you can use the machine learning notebooks, or you can use any IDE of your choice, like VS Code or PyCharms, and just standard build whatever you need to using the SDK. And a bit about how the AML service accomplishes this. So let's just take an example where we're trying to predict how much a certain car is worth. And oftentimes I know it's simplified, you have like 3 simple steps here, but you'll have some sort of like data preparation step, build and train step, and then deploy. So if you could simplify all those intermediate steps, it would look something like this. And of course, this whole process would be in like continuous loop, like CI/CD loop, which we also refer to as ML ops. So new data comes in, you build, train, evaluate, and then deploy. And that could be scheduled on like a monthly basis, weekly basis, or like a daily basis, time scheduled or human triggered. So in most cases, preparing the data it's not going to be in like a presentable format or a usable format. There's going to be missing data. You may need to combine data from different sources. And then perform some sort of like feature engineering and perform imputation to fill those missing values. Then you clean up the data and finally make it into something that you can work with. And your next step would be to do the building and training. And in this simple use case, we're back to the car value. Before even considering the model, you need to perform some sort of feature engineering, and you'll obviously want to know what your value or your target is. What are we trying to accomplish here? Are we trying to predict the class of the car, type of car, or are we trying to predict the value of the car? So in this case, it's the car value. So then you would have to think about like what type of algorithm am I going to use? Am I going to approach it as a classification type or regression type? And since it's going to be a continuous value, if you get like dollar value for the value of the car, then it's going to be a regression type operation. And that will influence some of the features and like the way you're going to modify these features. So in this case, we have car brand, year of make, and mileage. And right off the bat, I could tell just from like previous experience, it's very likely that the mileage of a car will have like one of the biggest impacts. And of course, there's going to be more features when you're performing machine learning, for example, like trim levels. And if you're living in like a cold climate, like in Calgary, maybe like an all-wheel drive system is favored over like a front wheel or a rear wheel drive. So that can drastically increase the value. So this is a simplified format, but in real situations, you may have as many as 30 or 40 or even more features. If you're working with IoT data, then you may have like thousands of features that you're working with, and all of this is complex, right? You really don't know like which feature is the most important, so you can use various libraries within AML. It supports all the open source libraries for evaluating like which features are important. You can pretty much perform your own code-based approach. Use, as I mentioned before, like use VS Code, notebooks, or other IDEs, and you can either execute that ML model in like a local, your local computer, or scale out with Azure ML Compute, whether it's like CPU-based or like GPU-based, depending on the type of algorithm that you're working with. So if you're working with, say, TensorFlow or something like that, and you want to use GPUs to train that your custom neural net, then you might want to spin up a GPU VM or a GPU cluster. Or if you're just doing some form of data transformation and you're working with lots of data, let's say like 100 gigs of data, obviously you don't want to do that on a single node. You want to scale up with Spark. And Spark is like a distributed computing framework. And you can use Databricks as a compute cluster, as your compute target, or use some other AML compute targets, and run your Spark code there, like your PySpark code specifically on those computes. And back to our car model. So when you're doing your building and training within AML SDK, on the x-axis here represents the number of runs, like the iterations of your model. And then Y can be whatever you want it to be, like some sort of evaluation metric. So since we're doing regression, let's assume this is like an R-squared value, or like an RMSE, like inverse a version of RMSE, where you're not looking at the error rate, but just the 1 minus the error rate in this case, just to match up with the scaling of this y-axis. And the point is that as you perform more iteration, you'll go from a metric score of, say, 45%. I'm going to say, like, just use accuracy just for simplicity's sake. So you start with 45% accuracy, and as you iterate and like discover more about your features and add in more data sets, you can finally get a more accurate model. And then usually, generally in machine learning, you'll reach maybe a target plateau value, and then you'll need to do more work, go back and like get better data, or like more data, or like if they're not labeled properly, label the data properly, and retrain to get higher accuracy. So as you have more iterations, generally your your evaluation metric will increase or decrease depending on if you're looking at error rates. Then that would decrease. It would be like the inverse of that. So lower iteration, you'll have higher error rate, and as you have higher iterations, that error rate will go down, and that will represent like a better performing model. And then finally, we have the stage where we're going to get to deployment. And for most purposes, we're going to be using Docker as our engine to create that image. And then we'll use that same engine on one of these devices. It could be an edge device, it could be on-prem or AKS. That's where that image will be running. And of course, that image will consist of like scoring scripts and all the other scripts needed to take a foreign incoming data and then score it against that model. And of course, the Azure Machine Learning, if you could summarize the three main benefits, is really you're just boosting your data science productivity by having these, the automated ML components. You have SDKs to quickly spin up compute as needed, depending on your work requirements. You don't have to go through the portal and spin up your own VMs. It does automatically. You just have to specify the type of VM you want and like the number of nodes, and it will spin up that VM for you. And it does all the engineering work in the background. For example, if you want to create a Docker image, you don't need to create the Docker make file. It'll do all of that work in the backend for you. So you're just essentially increasing the rate of your experimentation and just focusing on the data science aspect and not worry too much about the engineering that goes in the background. And then a bit about the automated ML, because I felt like this is something that anyone and everyone can make use of, whether you're like a manager or like just in sales. I think anyone can leverage this to quickly gain some insights from the data that you have. And as we saw that video previously, it's more or less point and click type approach. And we're going to go back to how much this car is worth type of or use case. And I guess it might be a little bit of a repeat of what I had mentioned before, but model creation is usually, for someone that's new, it might be a bit confusing. Like you don't know like which features to use or which algorithm to use or even like which hyperparameter to use within that algorithm. So if you're working with, say, like decision trees, we won't know which tree depth is the best choice. So what the AutoML does is gives you an option of using the UI. It can definitely be controlled through the SDK as well, but for someone that's using AutoML, maybe they would prefer to use the UI, where you pass on the data set and the engine will run several models, typically 40 different models, and find it'll score with different features and different algorithms and like different scaling wrappers for the data, and it'll get you a model with the best accuracy over time. So it'll run, say, 40 iterations of model training, and finally it'll find the best combination of parameters with the highest, I guess, the metric that you're tracking, whether it's accuracy or RMSE. It'll give you the one that has the best score in the end. So ultimately, it's really, the whole point is to accelerate the model development process. And then a lot of times, you may not even have to use code. You can just use the AutoML to perform most of your model training, given it's a simple use case with not too many features, and it's something straightforward. Like, for example, in this car value prediction type of approach, you can use the automated ML to predict the value of a car. And this slide here is comparing the two different models. One that has, let's say, 70% of a metric that we're tracking. Let's just say like accuracy. In this case, really would be the value of the car. So 70% accurate model of the value of the car. It's probably not selecting the type of feature. Maybe it's valuing certain feature too little. For in this case, it's valuing the condition of the car higher than even the mileage, and we know that generally like mileage would be one of the most important features. While car condition does matter, I think like the more well-tuned model has the appropriate feature importance. It's ranking mileage and like regulation, brand, condition, and so on appropriately. So the AutoML will sort of automate most of these components for you and give you like the best performing model. And you can use some of its pre-built libraries to have the model be explained for you automatically. So you don't have to go through the code and dig through why a certain model is performing a certain way, where using AutoML, it's more or less automatically done for you. And this was just one of the demos that I was going to show, like a computer vision demo. But we'll get back to that one. I'll just show like what the portal looks like first, and then we'll get back to some of the demos. So the way you can access this portal is by going through ml.azure.com, and then it'll more or less spin up that website that I was mentioning before. This is your main workspace for Azure ML. You can pretty much do full end-to-end machine learning within the single workspace. And just a bit of description of the workspace. So you have the three main components that I had mentioned before. You have your Python or notebooks. You have the automated ML component and the designer component. So this is like the three main components that comprise of the Azure ML. And you can see here all the computes that I have created or currently have. I have a CPU cluster and GPU cluster as well. And two actually, CPU notebook and GPU notebook, which are compute instances where it gives you your own personal data science workstation with all the libraries, data science libraries that you need pre-installed. And you can also have clusters, which are training clusters where you send most of the heavy workloads into this cluster, and it can have like multiple nodes. Right now it's not being used, so there are 0 nodes currently being provisioned, but as your workload ramps up, it may have 5 or 6 or whatever range that you set, and it'll automatically scale down depending on how much usage that cluster is being run at. And there are other assets as well. On the left pane, you can see that there's the 3 main authoring ways to use ML, Azure ML, and then there's also the assets. So you have your data sets, which are essentially, as the name suggests, you can create new data sets For example, this data set is the MNIST data set from a URL. And then you can register the data set. You can consume that data set through code. So you just copy this code, and then you can go to your either your VS Code, or you can consume it through your Jupyter notebooks. So this is like a Jupyter notebooks that's running on that workstation, on that compute instance VM. And then your experiments are all tracked here. So I've done quite a few experiments over the past few months, and I ran one experiment today. It's called SK-MNIST2, and all the information about that experiment that you run, whether you run it through the SDK, through AutoML, or through any other designer, all of that will be populated here. So you have like one universal tab that you can click on to view all your experiments, whether it's coming from a code or built in the UI itself. If you click on that experiment, it gives you some information, some metadata about that particular experiment. It gives you like the script that was used, the person that created this, the input, and various other metadata. For example, registered model, it's an SK-MNIST model, and some metrics. So you have accuracy and some other hyperparameters for the model that was used. And all the metrics are visible here. You can have it display as charts or table, and you can add more. You can track whatever metric that you want, and you can control that through the code. This particular model was built using code, the SDK. So you have more control over what you want to visualize, whereas the AutoML pretty much gives you every single possible metric that it could find. So you just get a bit more control of the type of model that are being built. And you can also see like the output logs of that model training run. You have all the metadata, like all the driver logs, all the I guess the containers that were spun up to train the model is also available here. And every kind of log that you would need, including like the actual model itself, is also available. You can download that model and then take it offline if you want to experiment with it further. Is available within the workspace. So you're just tracking everything that you do. You're essentially tracking it because you don't know when you'll need to go through a log and see a particular line that failed or that was working before but doesn't work anymore. So it gives you more control over some of the workloads that you're performing. And we have the concept of pipelines. And these pipelines are similar to your DevOps pipelines, but they're more specific for Azure ML. And so the pipelines, if I could click on one of these pipelines, they have, you can organize your full end-to-end workflow in what we call like pipeline steps. And this could be something like data ingestion and data preparation in one step. So this could be a single step here. And then a second step would be some sort of transformation applying. That could be an independent step on its own. And then another step where we do some sort of model scoring and evaluating could be separate steps. So you have more control over which steps we're running. And within that pipeline, you can create the individual steps as their own executable endpoint. So you can call that endpoint. In this case, it's a single step. Everything was performed in one step. But you could break that down into like 5-step, like model data ingestion, feature engineering as second step. Third step is model training. Fourth step is model evaluation. And fifth step is model deployment. So you can organize them into different categories and have like a modular design where you can deploy a given step as needed. So you don't have to perform all 5 steps. Maybe you want to do model retraining with a different set of parameters. So you can use the pipeline assets to break them into different steps and then only execute the retraining part and not the data ingestion part. So you kind of have like more control over which parts of your full pipeline you want to retrain or run again. And maybe you don't want to deploy to AKS. Maybe you want to deploy to a different service. Then you can run the first 4 steps and then change the last step where it would be deploying to like a different service, or go from like an ACI container instance deployment to an AKS deployment if that's what your workload requires. And of course, we have all of our models that we've trained registered here. So we have different versions for model. For example, SK-MNIST. It's the same one that I've ran 4 times. So we have like 4 iterations of that model. And you can either deploy that model or download that model. And if you want to deploy it, it'll ask you where you want to deploy it to. You can choose the endpoint, like container instance or AKS for deployment, and then you can pass on an entry script and like the dependencies files for like the Python libraries and so on, and just perform a full production grade deployment all within just this interface. And of course, the endpoints are some of our pipelines can be real-time endpoints for scoring, which I've trained and deployed on an ACI. And this endpoint is essentially that model that I trained earlier today. And if you were to hit this endpoint, it would return back with some sort of score. It tells you that this instance has 1 CPU and 1 gig of memory. So that's basically your model endpoint for scoring. And you can also have pipeline endpoints. So you can have all of those 5 different steps, data science, data model building, data feature engineering, and deployment steps as well. And you can trigger these steps as endpoints as well. So once that step is triggered, then it will perform whatever that your descriptions are in that step. And if it's only a deployment type step, then it will perform that deployment. Or if it's just a data ingestion or data preparation step, it will perform that particular step. And then in the compute, I sort of went over this previously, but there is the CPU notebooks, and then I just called it CPU notebook. You can certainly call it name it whatever you want. And depending on the type of workload, you can select a more complex CPU with higher RAM. If you're working with, say, sparse matrices, then maybe you need higher RAM on your compute. So you can choose a memory optimized compute, and you have the cost per hour. And you're only being charged for the amount of time this VM is running. So you can pick and choose how long you want to run this for. Maybe you want to do 2 hours of training on like a core, like a 20 core machine, pretty powerful machine with 1 gig of SSD storage, and then also 140 GB of RAM. So that's quite a bit of compute power to perform some sort of like machine learning operation, and the cost is about $1.50 per hour. So you can perform your model training and then turn off the VM or compute instance when it's not needed. So that's more about the compute types. There are a lot more different ones available. In this case, I'm just using the standard GPU, a single GPU instance, and for this, I'm using a CPU instance. And of course, the GPU will obviously have like a CPU there as well, fairly powerful CPU. And this would be for some of the like deep neural net training or some other, if I'm working with a lot of like matrices and like performing some sort of matrix optimization, maybe then I want to run that using like a framework that supports GPUs. And of course, the compute instance that has a fully dedicated NVIDIA GPU. And the cool thing is you can actually click on the Jupyter lab, and it'll open up more control over that particular VM. So it's just loading up that Jupyter environment, and you can more or less control it as if it were any other VM. So you have a terminal there, so you can look at the file system. Oh, this is a different terminal, Python terminal. So let me go back and let me close all of these and open up. Yeah, there we go. That's our interface. That's what it looks like when you first launch it. But since I was working on a few demos with the Jupyter notebooks, I couldn't quite see them. So you have different notebooks, Jupyter notebooks that you can just click and spin up. Empty notebook here. And you can also work through like a console, like command line if you wanted to, or use the terminal of that particular VM, and you can see just a standard Ubuntu type operations. You have all your files here. You can find out what kind of libraries you're working with by doing a standard pip freeze, and it gives you like all the libraries that come pre-installed with it. I don't know if you guys are able to see it. It might be a bit small, but yeah, you have more or less the most commonly used libraries are all available for you to use. For example, like TensorFlow 2.1 is like one of the earlier, later editions is available. So far, like I don't think I've ever needed to install any other library, but you may need to. You can also perform the OS level operations as well. So if you want to install, say, like npm, I think it's sudo apt-get install npm. I don't know if it has that, like Node Package Manager. Looks like it already has that, actually. It has npm installed already. So but if you do want to perform some other operations, like I want to have some other application or library installed, then you can certainly do that. It gives you full control over that particular instance, but it's really used more like a workstation, data science workstation, where you can either use Jupyter Lab, Jupyter Notebooks, or even RStudio. So this is like your standard Jupyter Notebook workflow, same as I was doing with the terminal. I'm going to go to my user, and then I'll have like all the projects that I'm working on. And you can open up one of those projects, like image classification part 1, which is going to be my demo. And and just use it as if it were any other Jupyter notebook that you may have been working with locally. And on that note, let's move. I'm going to close this and let's move on to the demo. So I'll just go to, I won't do the whole training from scratch. Instead, I'll just show you guys what I've already sort of done, because it does take 3 or 4 minutes to spin up all those resources and train. And for this demo, what I'm working with is the handwritten classification. So this is going to be a neural network that's going to detect handwritten labels. So for example, some of the handwritten digits may look like this. There's quite a few variations of this, and this is a commonly used toy data sets for building like basic neural nets. And then we're going to train that net to detect digits from 0 to 9 that are written by hand. So it's a very simple computer vision use case. And I'm going to go back and show you, quickly show you how that would look like. So the tutorials are all available for you to download. So if you want to click on, if you want to see how to get there, you can just click on the Azure Samples tab, and you have all the demos that I'm doing are pretty much available for you. You can clone these notebooks and start testing it out yourself. And so back to I'll open up my folder directory here, and back to this notebook. So I've set up all the prerequisites. I have imported some packages, created the workspace, set up the experiment, and attached an appropriate compute target. So this is already done for me. Like I already created that CPU cluster that you may have seen before. So it's ready to go, and I've already executed all the code. So this is more or less already executed. And here we're just downloading the data set into a local folder. Ideally, you want to create that data set within Azure ML, but in this case, I have the data set already downloaded. And we're just going to visualize some of the data. This is what it looks like. You have like various different digits and the labels associated with those digits. So it's pre-labeled data. So we're just going to perform a classification type, or train a classification type algorithm in our case. And we're training on that remote cluster, which is that training cluster that we created earlier. And you have some training script. I'm not going to go over this training script, but just know that it's type of model that's logistic regression model. So they're actually training logistic regression type model, not a neural net in this case. And don't be fooled by that regression. It is a classification type task because logistic regression is used to classify. So I think it looks like that's what they're using. So there are a few parameters there, like regularization rate and various other metrics that we're logging. So we're logging the accuracy and the regularization rate, and we're just dumping it into this output called the sklearn mnist.pickle file. And we have some other utility files to submit that training job, which you can more or less just get from this sh util, and then use that shell util to copy this util's Python script, which is more or less going to be very similar for most of the model training, and then submit that training job to that remote cluster. And it gives you some metadata of that job being submitted, and you can monitor that run as it's occurring. So in this case, it's showing me, I'm just running a simple widget here, which shows you all the logs. You can certainly view all these logs in the Azure ML Workspace. If you go back to like the the experiments, you can find all the metadata available there. But if you're working in like a development environment, like Python development environment, then you will get live results as that model is training. So nice little widget to give you like a visual representation of what's going on. And then you can get all the logs once it's completed that training. So it's creating some Docker image for training, and then Docker environment for training, and then running that script in that environment, and yeah, more logs there. And then finally, you get the final results. So you can get results of that run, and you'll see that accuracy is 92%, almost 92% accuracy for that classification task, and you can run more scripts or more commands to get all the file names that are generated there. And you don't need to worry about that. You can just use the SDK functions to register that model. And so we registered it as sklearn iteration 3. So it's the same model trained at like a few different times, and then the third iteration of the AMLS model. And then the next step would be to deploy that model, which I've also already done beforehand. And we have deployed this into an Azure container instance. And yeah, and then more workspace setup, few lines of code to set up the environment, very similar to the previous setup. And then you can import like all the libraries that you need. In this case, we're just importing like a PyPlot to build that visualization from the data that we're going to be scoring. And instead of having a training script, we're going to have a scoring script. And yeah, and then write those scripts to that directory again. And it takes about 2 minutes. In my current test, it took exactly 2 minutes and 34 seconds to perform that deployment into an ACI, a fairly slow ACI with like 1 gig of RAM, and I think it's a 1 gigahertz processor. But I think for test use cases, I think it's perfectly fine. But it's not doing any heavy lifting. It's just taking a data, incoming data, and then in this case, it would be that image of the digits, and then running that image through that classifier, that logistic regression classifier, and then it produces an output saying, I predicted this as a digit from 0 to 9. Like it's maybe, it looks at the image and then takes the pixels within that image and then makes that prediction. And then you can, of course, that endpoint that I was talking about earlier that was generated here, the endpoint, that would be this endpoint, real-time scoring endpoint that was created 2 times like earlier yesterday and like earlier today. And that endpoint can, with the appropriate like credentials, you can ping that endpoint, and then you get a result back. So if you pass on like an image of like a digit that you've hand drawn, then you can pass that on, and then it will rescale that image, score it, and then send it back to you, saying that this image is like anything from 0 to 9. And what we're doing here is creating that confusion matrix, and the confusion matrix is essentially all the true labels versus the predicted labels, and some of the error rates. It could be any metric, but generally, this is just a visual representation of this matrix here. So it's a way of visualizing which digits are performing well and which, or in this case, like which categories are performing well. So if zeros are always being classified as zeros, that's great. But maybe at times 8s can be misclassified as 0 or 9 or some other digits. So you can visualize of all the true values what are the actual labels versus the predicted value. So how does it match to the true labels? And that's one way of visualizing. Or you can just visualize using the PyPlot, and you can see all the digits from the current model. You can see that usually the 8, like in this case, 8, its actual value was 8, but the actual value, sorry, it was 2, but it was classified as 8, and then the real value was 6, but it was misclassified as 5, and so on. You can visualize some of the data there. And yeah, and ultimately, and that's pretty much, you just send your payload to that URL for scoring, or you can create like a AKS application that if you want to scale up, you can use AKS instead of ACI. And yeah, so submit that payload to that endpoint, and it returns with the result. That's pretty much like the basics of deploying the model, like the most basic model that we've deployed to that endpoint. I know that we've kind of like gone past our time allocation, but I did have another demo, but I don't think I'm going to go into that. I think it's fairly straightforward. If you have like the Azure ML samples, you can pretty much go through it yourself. This one was classifying. I was going to show you what like a credit card data. So basically, we have features, various features of credit card transactions, and what we're doing is using these like 28 features. And like the amount here is like, I think it's from a European region, so euros, 149 euros, and then the type of class is whether it's a fraudulent transaction or not. So most of them are not fraudulent transactions. There's only about, I believe, 400 or 500 fraudulent transactions, and this is like real life data, like real data that they've applied PCA, principal component analysis, on to sort of anonymize this data set. And yeah, you can start testing out that sample notebook with this data set, and all the links are available in those samples, and see how a classification works with AutoML. So I was going to do this all within automated ML using code, not using the interface, but with code. And you can pretty much select a few. It says easy, select your compute target. You can do it locally or select a remote compute, load your data, and then pass on some metrics. And yeah, you can monitor all the different models that are being trained on the fly. And just one more minute before I end this off, I'll show you guys what the results in the automated ML looks like. So this is the experiment, the automated ML executed from the SDK. So you can go there and then visualize some of the metadata. So it's taken about like 30 minutes to run this experiment, and you can have all the models that are being trained. Generally, it trains about, depending on how much timing budget you provide it, like if you give it like 4-hour training budget, then it'll continue training new models until it finds the best one. But in our case, all the models are performing pretty well. Like every single model it's performing near perfect precision score. So it ultimately uses the ensemble algorithm to take some of these different algorithms and then create like an ensemble model. And you can also view the explainability of that model. It's going to take some time to load, but let's go back to models and maybe take a look at one of them. So I'm going to go back to automated ML run one. So if you go to all the models that are generated, you can click on one of them and then it gives you more information about it. Like you can see average and like various other metrics, because accuracy may not be like the best metric to observe. Maybe you might want to look at like recall rate or like balanced accuracy. So balancing for both type of categories, both the not fraudulent cases to the fraudulent cases, because there's an imbalance. There's obviously a lot more fraudulent or non-fraudulent transactions versus only 400 fraudulent ones, whereas I think there's several thousand of those. So kind of gives you like a balanced perspective. And there's pretty much every single metric you can think of, it's available for you when you use the automated ML. And there's a lot more complexity to it, like the explain model tool, which explains why certain features were selected and why certain models were selected. So you can get like a full end-to-end explanation of how that works. And of course, you can download that automated ML. If you're satisfied with that accuracy, you can, of course, pretty much deploy all within this interface without having to do any kind of engineering work in the background. And that's pretty much all for the automated ML. And one last thing that I would go over is SSH access. So what I'm doing here is creating an SSH tunnel using like a private public key and just pretty much accessing that particular VM, that GPU VM, through VS Code. So if you prefer working with VS Code and don't like the interface that's offered in Azure ML, then you can certainly do so. And yeah, you can build all your models. So you can select the type of notebooks that you want to work with. It'll render it into like it'll render that Jupyter notebook format into one that's recognized within VS Code. So more or less, this is the Jupyter notebook environment. And you can select the IDE that it's running. And it gives you like a different way of approaching it. And of course, you have your standard console, which is the same console that I was working with. So you have all the directories. So Azure user, cloud files, users, PR, my username. And yeah, you can pretty much do whatever, all the operations, OS level operations through the VS Code extension, which is called the Remote Explorer. So it gives you that control over different flavors. I'm not sure about other IDEs, but it depends on the IDE. If it supports like FFH tunneling, then you can certainly use that IDE for development. And yeah, and that's all for my